Log on, tune in, find out. Another good idea from Cambridge.
I'm going to talk about work that I did in collaboration with Jan Lewis and Dan Waldram a few years ago, then another work where Aaron Sim was included, and then some more recent work in progress with Hagen Triendl, who's here in the audience. So what's the motivation to use, going back, what is the title, reductions with reduced supersymmetry using generalized geometry? What is the motivation to use generalized geometry in reductions with reduced supersymmetry? So I could say beauty, naturalness, unification, or things that you've seen that generalized geometry has, but let me be more precise. So we will discuss reductions of type 2 theories and M theory down to 4 dimensions. So these are done on 6 or 7-dimensional manifolds. And we will look for manifolds such that the effective action in 4 dimensions has a certain supersymmetry, n equals n. So in particular, I will talk about the cases of n equals 1 and 2. But most of the things that I will say up to the examples are general. So this effective action is determined by kinetic terms and potential terms. The kinetic terms are, so the action in the kinetic terms has a geometry of the moduli spaces, and these moduli spaces have a special geometry, and this special geometry is dictated usually by a single function. And the potential terms are encoded in the Gravitino mass matrix. For example, for small n equals 1, this Gravitino mass matrix is just a superpotential. So the potential is dictated by the superpotential. And what I want to show or convince is that generalized geometry gives expressions for these kinetic terms and potential or Gravitino mass matrix, or let's say for this single function here and this matrix or single function in the case of n equals 1, where there is a natural action of the duality group, or furthermore, actually these are invariant under the duality group. And what is this duality group? If we turn on the Ramon-Ramon fields, then the duality group is just T-duality, and this is the subject of generalized complex geometry. And then if we add the Ramon-Ramon fields, or we look at M theory, then one has to go to this exceptional generalized geometry that Dan talked about. And here the duality is U-duality. So you've heard this before, but it never hurts repeating a little bit. So how does it come, this T plus T star? One can think of it as encoding the symmetries of the NS sector degrees of freedom. So the degrees of freedom in the NS sector and the metric and the B field, the symmetries are diffeomorphisms that are given by vectors, or gauge transformation of the B fields that are given by one forms. This transform in the fundamental representations. If you combine these together on T plus T star, then you have these transforms as a vector of T plus T star. Then on T plus T star, there is a natural action of 066 if we're thinking about compactifications on 6-dimensional manifolds. And this 066 is the T-duality group, and this is the subject of generalized complex geometry. So generalized complex geometry is using complex geometry on this extended tangent bundle. This was well developed by Hitching and his student Gualtieri. Now, if we want to add the Ramon-Ramon fields and to this, so if we want to do some geometry such that the Ramon-Ramon fields are included, then one has to enlarge this space. And in particular, the way to see how to enlarge this space, we can again look at the symmetries of this. We have again the diffeomorphisms and the gauge transformation of the B fields. And then we have the gauge transformation of the Ramon-Ramon fields. And I will discuss here type 2A, but type 2B works similarly, just changing chirality. But in this case, the Ramon-Ramon fields are odd forms, so their gauge transformations are given by even forms. Now, we will work in the democratic formalism, where one considers all Ramon-Ramon fields. And these are, so all, let's say, even forms, sorry, all odd forms, that way, all odd forms in 10 dimensions. And this is, if we reduce to 4 dimensions, this gives us something that is closed under electromagnetic duality, while the rest is not closed under the electromagnetic duality. So if you just want to have something that transforms as a vector, that if you want to really fill up a representation of the U-duality group, you need to include the electromagnetic duals of these things. which are the electromagnetic dual of this B2 is a 6 form, and its gauge transformation is given by a 5 form. And then you need to include some sort of magnetic dual B-Elvine, that gives a Saclay monopole charge, and this is another one form. So if you combine all this, you get the T plus T star. Then here, this gives another copy of T plus T star. So 5 vectors and 5 forms, which on 6-dimensional manifolds, this is another copy of T plus T star, plus this S plus, which is the sum of all even forms. And if you count the degrees of freedom, you have 12 here, another 12 here, and these are 32, and this gives you 56, which is the fundamental representation of E7. So there is an E7 action on this extended generalized space, and it's natural to get E7 because this is the U-duality group for compactifications of type 2 down to 4 dimensions, as Dan mentioned. And this is the subject of exceptional generalized geometry that has been proposed by Hall and Dan and Pires Pacheco. And the same thing happens if you look at M theory. You again get this group. The only difference is that this is the splitting of the fundamental with respect to GL6 representations, and here the splitting will be different because the group that we will use to split is GL7. So if you look at M theory, the bosonic degrees of freedom are the metric plus the 3-form potential. The symmetries are again the diffeomorphisms given by vectors, and gauge transformation of the 3-form potentials, which are 2 forms. And again, we need to include their duals. So gauge transformations. So the dual of A3 is A6, as Dan mentioned, and its gauge transformation are a 5 form. Now, since this is a 7-dimensional manifold, this is equivalent to a 2 vector. And then here we have an extra 1 form. So we get a copy of T plus T star, but now this is a 7-dimensional manifold. This is a 7-dimensional tangent space. And then two vectors and 2 forms. And if you count degrees of freedom, you again have 56, 14 here, and then with the rest here. So again, there is an action of E7. It's just that the splitting is different because here we use GL7. So now we want to, so the particular thing I'm interested in is the compactification such that there is an effective theory in 4 dimensions that is supersymmetric. Then this means that there has to be some internal spinors defined. So if you have the 10 or the 11-dimensional spinor, in this case here I will talk about the 11-dimensional spinor, then you should be able to decompose it into some 4-dimensional spinor and some 7-dimensional spinor. And then actually, if you have n equals 1 supersymmetry, then this is it. If you have n equals to 2, you need to have 2 4-dimensional spinors, etc. So for n equals n supersymmetry, you have some decomposition like this, and this means that you need to have n internal spinors on the 7-dimensional manifold. So this n is an index of, so there is an SUN-R symmetry that rotates these n spinors. And the maximum that we can go is up to SU8. So this SUN is always a subgroup. Sorry, I should say equal here. If we look at n equals 8, it's a subgroup of SU8. So off-shell supersymmetry requires existence of these spinors. And this is some topological condition that says that the manifold, or let's say the generalized tangent space, has some reduced structure. So, well, Dan talked about it. We heard about this before, about the structure. So we need to have an SU8 minus n structure. So for n equals 1, we'll have an SU7 structure in E7. For n equals to 2, which are the 2 cases I will talk about in particular, we have an SU6 structure in E7. So that's the topological condition in order to have the action, the 4-dimensional action, to have some supersymmetry. And then there is some differential condition that I will not talk about. I will mention here and then at the end, which is that these spinors need to satisfy certain conditions, which come from requiring that the gravitino and the dilatino, the supersymmetry variations of the gravitino and dilatino are equal to 0. So this gives some differential conditions on the spinor, and they tell us about the integrability of the structure. But this is for vacua, for supersymmetric vacua. here I'm not interested, so I won't talk about supersymmetry back here. I will talk about just the action. And well, one motivation, so this is nice because this should allow the study of moduli spaces. Now so this was for 11, this was for M theory. In type 2 theories, we have two 10-dimensional spinors, epsilon left and epsilon right, but you can combine them into this doublet and write it as, so in terms of the 4-dimensional spinors and some eta and eta tilde, which are 6-dimensional spinors. But this is a spinor in 6 dimensions, so this transforms as an in SU4. This is another SU4, so this combined can be my thetas that transform under SU8. So these are 7-dimensional spinors that transform under SU8, and these are also spinors that, this is also some doublet that transforms under SU8. So I can say exactly the same for type 2 theories. There is this condition that there should be an SU8 minus n structure on this exceptional generalized tangent space in order to have the theory in 4 dimensions to have n equals small n supersymmetry. So now, given that there are internal spinors defined, one can construct bispinors, and this is the whole beauty of generalized complex geometry, or I mean it started from G structures. And these bispinors, they are very nice because they are bosonic. If you don't like fermions, these are bosonic. And then they carry all the information about the metric on the manifold. Usually these combinations of theta I, theta j, and we will see in the examples what particular combinations of theta I, theta j are relevant in each case. But they have all the information about the metric on the manifold. And then one can construct this dress by spinors, which is rotating these spinors by the action of the gauge fields. And this dress by spinors, so the gauge fields, if we're talking about M theory, this will be A3 and A6. If you're talking about type 2, this will be B2, B6, and Cn. And this is dc to the A, we'll see later, is in the adjoint of B7, dc to the A. So this is an adjoint action on these bispinors. And these dress bispinor carry all the information about the bosonic degrees of freedom, and these are the ones that describe the moduli spaces of the 4-dimensional theory. So if you want to let me jump ahead, these are like B plus Ij and then omega. So if we call this phi, we're going to call this phi and this phi dress. And what I want to show is that the moduli space metric, or the kinetic terms, are always given by some invariant function on the U-duality group, which is a quartic function. So this is some invariant of the U-duality group, and it's a quartic function of this dress by spinor. And then the potential terms are given by the Gravitino mass matrix, and this is some, again, invariant function, and we will see in the examples how this is. Some invariant function of this phi dress and then d phi dress. So these two, both these and these, are using expressions that are invariant under the U-duality group. So in particular here, if this is an invariant of the U-duality group, then this is the same as the undress 1 to the 4. So the kinetic terms don't depend, and the moduli space metric don't depend on these gauge fields. And then here, something one can do is, if here I have an invariant, then I can undress this spinor. I can act with e to the minus a, let's say, and then put it here. And then what you get is something like this. The mass matrix are always something like this. And this e to the minus a, d e to the a, is this twisted differential. For example, for the case of a being b2, e to the minus b, d e to the b is this twisted d plus h. And this happens in all the examples that we checked, and I think this is a generic phenomenon, that there's always, if there's some invariant function, then this is a quartic invariant of the U-duality group, and then the mass matrix is given by some invariant, but now this involves, so here I can undress the spinors, here I cannot because there is this derivative operator, but they're always given by things like this. So this is a lesson to take home, and if you have heard enough talks today, you can fall asleep. From now on, I will be more precise and be giving examples of this, how how does this work in n equals 1 and in n equals to 2 in type 2A and M theory. So I'll start by n equals to 2 reductions of type 2A. So now if it's type 2A, we are reducing on a 6-dimensional manifold. And again, if this is n equals to 2, then I have my spinor, my left and my right spinor. And then there are 2 4-dimensional spinors, and then 2 SU8 spinors, d theta. And the notation with respect to the SU4 spinors, you will see why I'm choosing eta and eta tilde, and here eta tilde and eta. So the bispinors that make sense to construct here are an SU2R singlet, which is this combination epsilon ij theta I theta j. This is an SU2R singlet, and an SU2R triplet with theta and theta bar, and then a poly sigma matrix. And you will see a little bit why these are the relevant bispinors. So this bispinor, so each spinor transforms in the 8 of SU8, so this thing it's antisymmetric in the indices. Let's say there's an index alpha and an index beta in the 8 and in the 8. It's antisymmetric in alpha beta because of this. So this transforms in the 28 of SU8, and the 28 embeds in the 56 of E7. So this bispinor is actually in the 56 of E7. While this one here has an index alpha up, let's say, and an index beta down, and it's traceless, so this transforms in the 63 of SU8, and this is in the 133 of E7. So these are in different representations of E7, this lambda and this k. Now, the notation here is such that if we take eta 1 tilde to 0 and eta 2 tilde to 0, then we read that epsilon left, or epsilon 1, is psi 1 tensor eta 1, and epsilon 2 is psi 2 tensor eta 2. And that's the usual n equals to 2 ansatz that we that people take, and we have taken before. So you will recognize things. If you have seen anything about generalized complex geometry, you will recognize everything here. So in this particular ansatz, which is some sort of the standard n equals to 2 ansatz, but it's not the most generic n equals to 2 ansatz, then here you have epsilon, theta 1 and theta 2. You have products of eta 1 and eta 2, and they are such that the chiralities, so the chiralities are such that you get phi plus, where phi plus is this eta 1, eta 2, plus dagger, and this phi plus and phi minus here in k plus. So if you do k1 plus I k2, you get the opposite chirality for, so this comes with the opposite chirality, so you get phi minus, which is eta 1, eta 2 minus dagger. And these are the famous, or well, I hope you've heard about them before, the pure spinors of generalized complex geometry. So you can think of this basically as the analog of phi plus and phi minus, the E7 version of phi plus and phi minus. And in general, the bispinors that we will construct are the equivalent of these pure spinors. And so what are these pure spinors? If you never heard about it, you can always do Fierce identities to rewrite this in terms of these bispinor indices here are the bispinor indices here in the gamma matrices, and then there's the Clifford map. You can replace these gammas by the x's, and then basically what these bispinors are a sum of forms, and each component of the form takes, so these sum of forms have all the bilinears of the spinors, eta 2 and eta 1. And in particular, if you take a particular case of eta 1 equals to eta 2, so which is perfectly fine here, you can take a spinor which is eta 0 and then 0 eta. That's a valid SU6 structure in E7. And this is the case of a Calabi-Yau manifold where you have a single spinor on the a single globally defined spinor on the 6-dimensional space. Then what you get is that phi plus in the bilinears with an eta plus and an eta plus, only an even number of gamma matrices appear, and what you get is e to the ij. Where j is a fundamental form of the Calabi-Yau manifold that Xenia called little omega this morning, so some people call it little omega. So phi plus is e to the ij, and phi minus is omega 3. So these are the holomorphic, the 1-1 form and the 3-0 form of the Calabi-Yau. So you should think of this lambda and k basically as e to the ij and omega, or I mean some E7 version of e to the ij and omega. So if we are in reductions of type 2a, so e to the ij is in vector multiplets, while omega is in hypermultiplets, and then it makes sense that this is an SU2R singlet and this is an SU2R triplet. You know a little bit about n equals to 2. So now if we construct a dress by spinor, then this means adding the other bosonic degrees of freedom. So these spinors here, they define, the spinors here, they define the metric. E to the ij and omega define the metric. Now if we want something that combines all the degrees of freedom in type 2, then we need to build this dress by spinor. So dress is with B2, B6, and C, which are all E7 adjoint elements. And in particular, the way they embed in E7 is, so E7 here, if we want to see how generalized geometry arises, a subgroup that we should look at in E7 is SL2R times 066. And then, so the fundamental of E7, which is the 133, so these are all in the, the fundamental, the adjoint, these are all in the adjoint of E7. This breaks into the adjoint of SL2, the adjoint of 066, plus this extra bit. And then in the adjoint of 066, we have here the diffeomorphisms, and then the B transform that Magdalena talked about this morning. So this is how B2 is embedded here. Then B6 and the Ramon are embedded in the other pieces of, so they are not in the adjoint of 066, but they are B6 is in the adjoint of SL2R, and then the Ramon fields is in one of these 32. So this BI is some vector in SL2 pointing along some positive route. If you know something about this, you will make sense of this. This is the geometric subgroup, and this is the subgroup by which we are allowed to patch the generalized tangent bundle. This is some parabolic subgroup, and particularly the nilpotent subgroup of this geometric. So if I take the diffeomorphisms to 0, then these are the shift symmetries. So B6, B2, and BI, they form some nilpotent subgroup of geometric, and this is always the same. And then the rest are the hidden symmetries, which are, well, they were called hidden symmetries, I think, by the supergravity people. These are just T or S duals of the shift symmetries. In particular, for example, this beta that Magdalena talked about, which is a T dual of B. And if this sort of hidden symmetry have a global flux associated, then this is something, well, these are the non-geometric backgrounds. So out of these 133 elements, we have the diffeomorphisms. So going back, we have the diffeomorphisms, the B2, the B6, the C field, and then all the rest that is not here are these hidden symmetries, like analogs of. So here, for example, I have, this is a sum of all forms pointing along the positive root, pointing along the negative root, the doublet of this. There's a sum of odd vectors, multi-vectors, and these are so play the same role as the beta transformation plays in generalized geometry. So now now if I build this dress by spinor, e to the B, to the B6, e to the C, on lambda and K, these objects carry all the information about the metric, the B field, and the C field of the manifold. And these are the objects that appear in the effective action in 4 dimensions. So in particular, let's look at the moduli spaces, and let's just first do generalized geometry. So let's turn off the Ramon fields, and let's review what this was done by Hitching. What is a moduli space? What are these variations of delta phi dress, where delta phi dress, so these are the pure, I'm using phi for just a pure spinor, phi plus, so e to the ij, with e to the b, this is e to the b plus ij. Now this is actually, this moduli space is actually fully defined, or the full pure spinors is actually defined if you take only the real part of the pure spinor. And this defines this is stabilized by an SU33 structure in 066. So this defines an SU33 structure in 066. So this the action of 066 on this spinor makes up this orbit, which is 066 divided by SU33 times R plus if you consider rescalings of phi plus. And this space is in this special Kähler, and the Kähler potential is given by the Hitching functional, which is the quartic invariant of 066. So indeed, as I said at the beginning, what happens is that these Kähler potentials are given by quartic invariants, and in this case is the Hitching functional, which is, well, the details are not very important, but which can be written like this, where these are the 066 gamma matrices. This is the Mukai pairing of forms, which is the invariant, the symplectic invariant top form, which is in the spinor language. This is what corresponds to the spinor bilinear, and these gammas are by the Clifford action. The details are not important, but just if one writes this in terms of the complex spinor, these things define the imaginary part of the spinor, and this is nothing but phi plus bar. This is the Mukai pairing of phi plus and phi plus bar. And since this is an invariant, this Mukai pairing is an invariant of 066. As I said, this is the dress spinor, but then you can, this is dress means by an action of 066, and this is invariant under this action, so I can take this away. So what I get is phi plus bar, and this is nothing but J cube. So after all this song and dance, we recover the Kähler potential that we knew had to be, that arises in Calabi-Yau manifolds. So this arises in any manifold. So I'm not saying anything about the integrability of these phi plus and phi minus, but any manifolds where one can define this single spinor, they have this Kähler potential given by the quartic, the Hitching function, which is the quartic invariant of 066. Now, if we turn on the Ramon-Ramon fluxes, if we do exceptional generalized geometry, this phi plus is in vector multiplets, and so we said that instead of phi plus, what we have is this bispinor lambda, and this defines an E6 structure in E7. And indeed, this space, so this moduli space is going to be E7 over E6 times R plus, and this space is indeed special Kähler, and the Kähler potential is, so this was found in the early 80s and in the 90s, and the Kähler potential is given again here in this case is the quartic invariant of E7, the square root of the quartic invariant of E7. And now if you use this particular ansatz where the tilde spinors are equal to 0 and lambda is just phi plus, what you get is exactly the same as before. But now this is defined by some quartic invariant of E7 instead of some quartic invariant of 066. And that will happen every time that these Kähler potentials are defined by some, or at least every time that we try it, and I think this is generic, that this is some quartic invariant of the group. So while for hypermultiplets, so delta phi minus, which is omega, is part of hypermultiplets, and this is if you just have phi minus, this builds some special Kähler manifold, and the Kähler potential is given by the Hitching functional, the same as for phi plus. Now, if you add the Ramon-Ramon fields, we said that phi minus is embedded in this triplet, in the 133, and this, what we expect, we are supposed to get quaternionic manifolds out in the hypermultiplets. The moduli space of these hypermultiplets have a quaternionic geometry, and indeed, these Ka are stabilized by this SO12 times SO2, so they, or SO12, let's say a single Ka, and so the moduli space or the orbit of these Kas under E7 is this group E7 over SO12 times SU2, and this is indeed quaternionic, and indeed how one can go from this special Kähler submanifold of the quaternionic space is via the CMAP, and indeed Cecotti, Ferrara, and Girardello and the Witt and Van Proyen show that this space is in the inverse of the CMAP of this space, of this 066 by SU33 times U1, which was the moduli space of this delta phi minus. So everything works nicely. And then over this quaternionic manifold, there is a hyperkähler cone if you add the compensator. And these hyperkähler manifolds are, well, these Ka are the triplets of complex structure. These hyperkähler manifolds are nice because they are described again by a single function, which is a hyperkähler potential. And given this triplet of complex structure, the hyperkähler potential is something like this. And again, if we insert this particular K plus, what we get is again things like omega, omega bar, square root of omega, omega bar, which agrees with what Rocek, Baffa, and Van Doren found in 2006, that this hyperkähler potential should be this e to the 1/2 K minus, where K minus is the Kähler potential for this space. So again, this again here things here are determined by invariance of the duality group. And then the potential, which is encoded in the gravitino mass matrix. This is in the case of n equals to 2, this is a 2 by 2 matrix. And this is, we found in 2005 that one can write this nicely in terms of this dress by spinor. In this way, the way I showed at the beginning, phi plus d phi minus with some invariant. Here the invariant is a Mukai pairing. And here we have phi plus d phi minus. And then the Ramon-Ramon, since in generalized complex geometry, so this is for using generalized complex geometry. In generalized complex geometry, the Ramon-Ramon are not inside here, so this phi dress has only e to the b inside, so the Ramon-Ramon appear explicitly here. While the H flux is indeed, as I said at the beginning, the H flux is encoded in here. So we said this phi dress and d phi dress, so this e to the, here this has an e to the b, this has an e to the b, this e to the b, I can act on e to the minus b in this, and then build this twisted differential operator. So the H flux is encoded in here, but the Ramon-Ramon flux is not encoded in here. It's there. This also has some nice generalization. If we're so, actually the Ramon. So we have some purely geometric description, something like this. But if we go, in order to do that, we need to go to exceptional generalized geometry. And what has some nice description are these, they're called the Killing prepotentials, which is just, it's the elements of this matrix. So we use Pauli sigma matrices to write this as a triplet of elements. And this triplet of elements, so P plus and P minus are, P plus and P3 are this. So here you can read P plus and here you can read P3. And these are the description in exceptional generalized geometry is given by the symplectic invariant of E7 of lambda decay. So again, we have, as I said at the beginning, we have some invariant of E7 and then the structure and then D of the structure. So here there are two structures, lambda and K, and so what we get is symplectic invariant of lambda and decay. So this S is a symplectic invariant, and then D here, it's a, so you need to, this is some symplectic invariant, this is an object in the 56, this is an object in the 133, and what happens here is that D is actually embedded in the, so D in the case of generalized geometry, D is in the 6 of 06, this is embedded in the 12 of 066, and in the case of exceptional generalized geometry, D is going to be embedded here in this 212, so it's always in the fundamental of the group. The fundamental here is a 12, here is a 56, but you see in this particular bit, 212 bit, and it turns out that it has to be again given by a positive root. So this B is the same as the one that selects what the Ramon-Ramon fields are. But again, these are how you embed this, and so what you get, the important lesson is that you get some invariant of the group, and then the structure, and then D of the structure again. Here we have two structures, so we get the structure corresponding to vector multiplets that doesn't appear with a derivative, and then the structure that corresponds to hypermultiplets that appears with a derivative. Now, if you do reduction, n equals to 2 reductions of M theory, we have something very similar, but there's something very nice here that I want to show you. which is the following. Instead of using SL2R times O66, let me use SL8 decomposition. And then you will see that there are some nice sort of 8-dimensional structures that appear if you use this SL8 decomposition. So this SL8 acts on some 8-dimensional tangent space that one can think of. This is just the 7-dimensional tangent space of the manifold, plus some extra direction related to, if you want, a volume of this 7-dimensional tangent space. So any element of the tangent space or on the dual tangent space can be decomposed into some component here and some component here that we'll call rho 8. And the fact that there are two spinors, one can construct a bilinear of these two spinors, and this gives me a vector. And so this means that the 7-dimensional space, it's not necessarily a sum, but it can be a fibration, but it's sort of decomposed into some 6-dimensional space plus this vectorial direction, which is given by the bilinear between theta 1 and theta 2, and then this T rho 8. And then with this decomposition of 6 plus V plus rho 8, I can do nice things with this lambda and K. So the same thing, this is an M theory, but actually the relevant objects are again this lambda and K, this SU2R singlet and this SU2R triplet. Now, as I said, I want to look at SL8 decompositions, and the 56 decomposes as 28 plus 28 prime. These are two vectors on the 8-dimensional, on this 8-dimensional tangent space, and these are two forms on the 8-dimensional tangent space. And if you look at what these two vectors and two forms are by, again, doing, so these contain all the bilinears of the spinors, then what you get is that the two form can be written as J8, and the two vector is sort of the 8 dimension. So this is a two vector dual to J8 cube, where J8 is J plus V wedge rho 8. So these two extra directions, so some sort of J that one can think of on this 6-dimensional manifold, and I can think of a J as being in the 6-dimensional manifold because one can show that the contraction along this, the dual vector to V, the dual vector to this one form of J is equal to 0. Now this J is not the typical, so whenever we have some, well, usually the J that we're used to uses let's say in the case of 6-dimensional manifold, it uses SU4 spinors. Now this uses SU8 spinors, but then also it uses bilinear with two different spinors. So using this J as a bilinear with two different, so between theta 1 and theta 2, these two form, then I can write this lambda in terms of this sort of 8-dimensional J. While here, the K, which is in the 133, and if I decompose this in SL8, this is in the 63 plus 70. The 63 is the adjoint, so tensor times one form and taking traceless, and then the 70 are 4 forms on the tangent space. Then if I look at this, what are these forms in terms of SL8 of this SU8 object, what I get is that it has nothing on the 63, and it has a 4 form here, which I can write as omega 4, and omega 4 is basically what you expect. It's omega 3 wedge rho 8 plus IV, and omega 3 is this bilinear with 3 gamma matrices. So this looks very much like some SU4 structure on this 8-dimensional space. This lambda and K look very much like the e to the ij and omega of this 8-dimensional space. So that's something nice. And indeed one can show that J wedge omega is equal to 0. J wedge omega 4 is equal to 0. And what about the dress by spinors? So dress by spinors, again, I have to dress them or rotate them by the action of the gauge fields. So A and A tilde, I'm using the same notation as Dan used. A is the 3 form, and A tilde is the 6 form dual. These A3 and A6 are in the adjoint of E7, and I do the same for lambda and for K. And in terms of SL8 decomposition, so in terms of SL8 decompositions, they embed like this. So in terms of SL8, the 133 again decomposes as 63 plus 7. This is the adjoint of SL8. and these are 8 by 8 matrices. These 8 by 8 matrices, if you decompose them with 7 by 7, and then a file, and then a row, and then a column, then these 7 by 7 matrices here are the diffeomorphisms, and what you get here is that this is a row with 7 entries, and this is the 7-dimensional dual of A6. So this A tilde is A6, this is the 7-dimensional dual of A6. So X6 embeds in here, while A3 embeds in here as this 4 form. So we can think of, we can think of this as a 4 form along row 8. So A3 is like some 4 form along row 8. So again, this lambda and this K dress carry all the information about the metric and the gauge fields on the manifold. And something nice, again, that if you look at lambda, which was the thing, one can write this as the action of this 4 form, J, wedge B, wedge row 8. This is the adjoint action in E7, but note that this is imaginary, so this is not like in E7 rotation, but it's some E7 complex action on these 2 vectors. So this row 8 hat and B hat are the dual vectors to row 8 and B. And so one can write this as this action on this row 8 hat plus B hat, and then when you act on this with this 3-form potential, then what you get is something like this, e to the A4 minus this, and this is very similar to e to the B minus ij. The structure is very much like e to the B minus ij, but now you have 4 forms. So, and again, if the moduli spaces are again given by the, so I said this before for the type 2, this was given by the square root of the quartic invariant specialized on lambda, but if we use this sort of SU4 structure in 8 dimensions, then what you get is precisely what you expect, J8 to the 4, J8 with J8 with J8 with J8. This is the Kähler potential for the vector multiplets in terms of this. And for the hypermultiplets, what you get is again what you expect, square root of omega 4 with omega 4 bar. So I think, well, this is very nice. That in M theory one can do this sort of 8-dimensional geometry. And then as a last example, I'll talk about n equals 1 reductions of M theory. This was actually mostly done by Dan and Pires Pacheco, but then we continued a little bit with the Kähler potentials. And here there's a single spinor, so the bispinor, then one takes a bispinor, tensor in the spinor with itself. This is in the 36, so this is symmetric. You take the symmetric combination, and so this is in the 36 of SU8. And this embeds actually in a much larger representation, which is the 912 of E7. So in n equals 1, the relevant object is some phi, which is in the 912 of E7. And the 912, with respect to the decomposition under SU8 or SL8, which has the same, under SU8 or SL8, you have the same representations, splits like this. And in particular, so there is this symmetric 2 tensor, and then there is this 420, which is a 3-form tensor, some vector, and the same for the 36 prime and 420 prime. It's the same with the indices up. And in particular, if you look at this object here in SL8, which you get by doing bilinears of the spinor with gamma matrices, what you get is I didn't write it. What you get is some 4 form, which is the analog of the 4 form of, so it contains the 3 form of a G2 structure. So this alpha 3 is the bilinear with 3 gamma matrices. So this object in the 912 contains information of some, so this is the analog of a G2 structure. So this bilinear in the 912 that is relevant for n equals 1 reductions of M theory contains this information about this, this 4 form, which is like, so typically 4 form will be like this, so here we get an additional term along this row 8. And the moduli spaces, so here we have a single object in E7, so this defines an SU7 structure, so, or it's stabilized by SU7, so the variations span this space, which is Kähler. The Kähler potential is given by the quartic invariant, but Now, so the quartic invariant of E7, but this is the quartic invariant on the 912. And indeed, what you get is something like 5,4 with 5,4, which agrees with the G2 structure expression. Where 5,4, here I wrote it, 5,4 is a bilinear with 4 gamma matrices. And so this is as in the G2 structure. And then the n equals 1 superpotential, you can get it from this eigenvalue equation, d phi. If you project it on phi, then you get, d phi E7, so this is something in the 912, this is something in the 912, and if you take the thing, so you use this phi sort of to project out on the singlet, and this singlet is a superpotential, and what you get, so now this d is the same as before. This d is embedded. Before it was embedded in the 212 with respect to SL2 times 066. Now this is embedded in the 28 with respect to 28 prime with respect to SL8 as a 2 form, and this is it's a 2 form along row 8. And then doing this, what you get is this nice expression in terms of 5,4 complex, which is 5,4 plus IA4, where A4 again is A3 wedge row 8. So you get expressions which are very similar to, I didn't discuss n equals 1 on type 2, but they are very similar to what you get in n equals 1 in type 2. N equals 1 in type 2, you get some combination of phi and the Ramon fields, and here you get the same. So you can wake up now again. So to conclude, and I'm early, but that's good because it's the last talk. We all want to go to the drink reception. Generalized geometry. So generalized geometry gives a nice description for reductions with reduced supersymmetry. All the relevant degrees of freedom are contained in these dress spinor bilinears, and the special Kähler and quaternionic moduli spaces of n equals 1 and n equals to 2, they're always they're given by the orbits of this bispinor and the reaction of the duality group, and the Kähler and hyperkähler potential, so these are described by a single function, and this single function is some invariant of the duality group specialized to this orbit. And the Gravitino mass matrix is always again given by some invariant of the group of something like, which is always like phi d phi. So something that I didn't tell you, but supersymmetry vacua is typically related to expressions like this, phi being some integrable structure. So I think, well, generalized geometry, you've heard enough today to say that generalized geometry is tailor-made for supergravity backgrounds, and in particular reductions with supersymmetry. And the question that I think one of the most important questions, which was the subject of the previous talk, and it was also discussed by Dan, is what happens with the corrections. And in particular, in the case of reductions with supersymmetry, since everything is given in terms of invariance of the group, we might expect that this should help finding the corrections in some, again, invariant of the group. But so this is in the future. Thank you.
Any questions?
Yes, in the type 2 case, shouldn't you impose a self-duality condition at some point?
At the level of 10-dimensional, yes, but at the level of 10-dimensional. Then when you're in the reduced theory, so you mean for the Ramon fields?
And also you added some these dual fields.
Yeah, so at the level of at the level of the 10-dimensional fields, you have this, well, with signs, but basically the sum of these forms is this is the sum of all the Ramon forms is self-dual. But then when you're at the level of the 4 dimensions, then this is not self-dual. At the level of 6 dimensions, this is not self-dual anymore. So what you get is, well, for example, if you want to preserve Lorentz invariance in 4 dimensions, this is if it has some component in 4 dimensions, it should be proportional to volume 4, and then some f tilde, and then plus some internal f. And self-duality relates these two. Sorry, this self-duality relates these two. But I'm talking about these things here. So, and also the Ramon. Sorry, maybe. So maybe you're confused because I said that this was a closed set under electromagnetic duality. So typically, for example, in type 2A, one would consider so A1 and A3, so giving F2 and F4, and that's it. But what I'm going to consider is also F5. Given this, I don't know if I'm being very clear, but I'm using this democratic formulation that considers all the Ramon-Ramon potentials or all the Ramon-Ramon fluxes, and these are self-dual. These are self-dual in 10 dimensions, but then now they are not self-dual in 6 dimensions, but they are. I mean, in terms of the 4-dimensional theory, these are the electromagnetic duals. So if you want some electromagnetic duality invariant formulation, you need to include also A5 or C5 or C5 in the. You don't seem very helpful. We can discuss more.
Any more questions?
Maybe you said this and I missed it, so I apologize. But when people use generalized geometry in the usual sense, and then they had generalized Calabi-Yaos and stuff. So can you come up with things like generalized G2?
Yes.
And then it's you get the sort of G2
So,
put with the thing.
Yeah. So that would be this for this object in the 912. Yes.
Any other questions? If not, let's thank the speaker again.